Hi, can everyone hear me? There's a little Zoom chat button. If anyone's having any problems, then type it into the Zoom chat screen. So everyone, welcome to Synchrotron X-rays for micromechanical analysis. My name is Darren Pagan, and I'm a staff scientist here at Chess. So today I'm going to cover, today's going to be an introductory lecture, and today I'm going to be talking about what's a synchrotron, and why do we use X-rays? Specifically high energy ones. 301. And then we're going to do a little bit of a continuum mechanics review. And we're going to be talking about coordinate transformations. Hopefully, the continuum mechanics review and talking about coordinate transformations, hopefully that's a review. But we're going to be using it a lot during this course, so I wanted to go over it just to start off. So in this class, when possible, I'm going to be using direct notation instead of indicial notation, but sometimes I can't escape that. So if you need help with indicial notation, send me an email and I can send you maybe some links or some review chapters. And when possible, I'm going to try to provide equations in matrix form, because in this class we want to be talking about data analysis, which these days means there's going to be a little bit of programming happening. If you're programming, you're probably going to be working with matrices a lot. I mentioned it previously, but there's a Zoom chat window. If you look in the app somewhere, there's a chat button, and that'll bring up a chat window. If you have questions, type them into the chat window, and we have someone here watching out for those, and they'll stop me and we'll try to answer the questions. The lectures should be posted online later, and I'll send an email out as to a link to them. They'll probably be on YouTube Live. So in the title of the class here, we've got micromechanics. So we're talking about mechanics, and specifically this is about solid mechanics. There's a couple of big questions that I think we're always asking. Also, as I'm doing this, can everyone read the text on the screen here? If there's a problem, also type that in. So, I think the most important question, talk about solid mechanics, is what is the distribution of stress? So stress is a second order tensor. We're going to be talking about stress later on in the class, but stress drives deformation and stress drives material failure. So those are big, interesting questions that we want to get after using X-rays. Second big question. So what are the constitutive equations that describe the deformation? Can we come up with equations that describe how stress drives how a material deforms, so how its shape changes and how its internal structure changes? And our bonus question for the engineers is, what are the failure criteria? So this is the big question for an engineer, is can we figure out when something's going to fail and how it's going to fail so we can design for it? So at the micro scale, the answers to these questions is tied to what I'm going to call the microstructure. So this is important. If we want to understand the answer to these questions, we're going to have to figure out information about the microstructure. So that's kind of going to be one of the big goals of this class, is how are we going to use X-rays to understand the microstructure? And by microstructure, I mean things like the distribution of crystal orientations, that's referred to as the crystallographic texture. So most materials are polycrystalline. They're made out of collections of crystals. And so the distribution of orientation of those collections of crystals is a big driver for the micromechanical response. Grain morphology, so the size and shape of the crystals that make up our material. The distribution of secondary phases. If you've got a material that might have two phases present, how those phases interact is very important, and just how they're arranged. Precipitates. small voids and cracks. And the dislocation, content, and character. So, different X-ray techniques have been developed to understand and determine all these quantities from X-ray data. What's important to remember, and the purpose of this class, is the only thing that we measure here are distributions of X-rays. So, to get from these distributions of X-rays to those quantities about the microstructure that I was just talking about, we're going to need models and lots of data processing. A lot of the X-ray experiments that we do are actually fairly straightforward. Where things get very complicated is how we process and interpret that data to get the quantities that we want. So my last bit is that these models are usually combinations of solid mechanics plus the X-ray physics. Usually in the presentation of these materials, it's X-ray physics first and solid mechanics as an afterthought. This class is going to be presented with solid mechanics first, and that's going to tell us what we want to know and drive us for understanding the X-ray physics to get to the information that we want. So that's it for my introduction about micromechanics and what we're trying to do in this class. And so I'm here situated at CHESS, and CHESS stands for the Cornell Highenergy Synchrotron source. Some of you might not be familiar with what a synchrotron is. And what does it have to do with X-rays, and what does it have to do with studying things like metals or other structural materials? So the synchrotron is a particle accelerator. It's a particle accelerator that what makes it special is that as the particles are accelerated, there's a set of magnets which bend the beam, which bend the particles around a ring, and that the increase of the strength of the magnets is synced to the acceleration of the particles so that the particles can move in a fixed radius. That's where the sync in synchrotron comes for. Once the particles are accelerated, they're moved into a storage ring. And we harvest the X-rays that are emitted from the particles as they move around in the storage ring. And there's here at CHESS and at most synchrotron sources, there's two ways that that's done. The first is add a bend magnet. So I've said that the particles go around a ring. But in reality, if we zoom in on a little piece of the ring, what we'll actually find is that the ring is made up of straight sections and bends. And at each of these bends, there's a bend magnet. Now, as an electron or a positron goes through the bend magnet, there's a field here. In this case, it's coming into the board. And as it passes through the field, it turns. But as it turns, it's accelerating. So it's not getting any faster, but it is changing directions and accelerating. And it'll kick off a beam of light. Now, these particles have high enough energy that this beam of light, most of the photons are in the X-ray regime. There's some in the high UV range, there's some in the gamma ray range, but the sweet spot for this is in the X-ray range. So with these tangential X-rays, we can build a beamline, place our sample, and then use these X-rays to probe our sample. The other way that we use the electrons going around the beam, or going around the ring, is with what we call an insertion device. And these are called either undulators or wigglers. And these names are actually fairly descriptive, and you'll see in a sec. So I said that we've got straight sections, bend magnets, and turns. But we can also insert a device into the straight section, which is actually, see if I can draw this, just a tightly packed series of magnets in a line. And what happens is, as the electron goes through, these tight set of magnets cause the electrons to oscillate back and forth. And now it's accelerating back and forth very quickly. and a boosted beam of light is emitted from the insertion device. And you can see here that the insertion device is causing the electrons to undulate and wiggle inside, so that's where the name comes from. There's slight differences between, not slight, but there are differences between the two, which I'm not going to get into today. So what's special about these beams? The X-ray beams at a synchrotron source are brighter than a lab source. So what do I mean by that? So there are more photons or flux. There's less divergence. You can also think about that as the spread, is that these X-rays are very collimated. And the source is smaller. So all these X-rays are emitted from a very tiny particle beam. And optics-wise, it's much easier to focus the X-rays from a small source. So if you want to use X-rays, the beams that come out of a synchrotron are very specialized and they're very valuable for these reasons.
I have a question. So
Yeah.
are the bend magnet and the undulators and wigglers, they're in the synchrotron ring and not in the storage ring?
They're in the storage ring.
They're in the storage ring.
Right.
Okay.
So the particle beams are accelerated in the synchrotron, and then they're moved over to the storage ring.
That's when you have the bend, you get the X-rays into the house.
Right. The synchrotron also has bend magnets, but we use the bend magnets that are sitting in the storage ring. The last thing is if we've got a specialized synchrotron. So if the synchrotron can accelerate the particles, either the electrons or positrons, to very high energies, something like greater than 5 giga-electron volts, we end up with this characteristic spectrum of the X-rays emitted from the ring that looks something like this. So on the left side, we have the number of photons. And the bottom, we have X-ray energy. A spectrum that looks kind of like this. kind of peaks out somewhere around 10. But what's important is that if you go out to about 10 kiloelectron volts, so this is a way of describing either the energy or the wavelength of a photon. We go out to 30 kiloelectron volts, we still have a significant number of photons out here. And what's important is that these high energy photons, so that's what I'm going to use kind of as the rough definition of what a high energy X-ray is, 30 kiloelectron volts, we're able to penetrate through materials with atomic numbers greater than 20. So we're able to, at about 30 kiloelectron volts and above, we can start getting through millimeters of materials with atomic numbers greater than 20. And there's lots of structural materials that we're interested in this range. Things like titanium, iron, copper, and nickel are all in this range. So I've talked a lot about how nice the X-ray beam is here, or at other synchrotron sources. But why X-rays? What we can do is we can compare it to other often used penetrating probes. This list isn't going to be exhaustive. So we often use electrons. We've got X-rays, or we use neutrons. Electrons interact strongly with the electromagnetic field since it's a charged particle. And if you interact strongly with electromagnetic fields, you also interact strongly with matter. And that's bad for penetrating through materials. So electrons have low penetration depth. However, since they also interact strongly with electromagnetic fields, they're fairly easy to focus. So you can get great focusing with electrons. So you can look at very, very small spots. X-rays have moderate interaction. Mid-range penetration. And we can focus them, but it's moderately difficult. So it's very hard to make very small X-ray beams in the nanoscale range. Neutrons have weak interaction with matter. which means they can penetrate deeply into materials. But they're very hard to focus. The great thing about neutrons is they go through everything. The downside of neutrons is they go through everything. They're also very hard to detect. But these properties kind of give natural size scales that they're good for looking at, or what they're optimized for looking at. So electrons are great for the atomic scale. And looking at things in high resolution. X-rays are good at the micro scale. And neutrons are great at looking at the continuum scale. So looking at things like full-size parts. What's important is that these are not hard and fast rules. You can make very small X-ray beams. You can slit down neutron beams to look at small volumes. You can also have large scanning microscopes to look at larger volumes. But just generally, what really each thing's strong suit is electrons are good at very, very small things. X-rays are good kind of in the middle, the mesoscale or the microscale, and neutrons are great at the continuum scale. So this class has microscale in the title, so we're kind of going to be working right in the sweet spot of what X-rays are good for. So, talked about synchrotrons, and I've talked about why we're going to use X-rays. And now, we're going to kind of start getting into the meat of the course. So in the beginning, I said the next topic that we're going to be talking about is we're going to go through a quick continuum mechanics review. And specifically, we're going to be talking more about kinematics. So we're going to be talking about descriptions or ways to describe a deforming body or a deforming material. Now we don't have questions. So, why are we talking about continuum mechanics and why are we going to talk about deforming bodies? The reason is later on in the class, we're going to be modeling diffraction experiments and we're going to be modeling deformed materials and how they interact with X-rays. So what we're going to be using is we're going to be using some of the tools from continuum mechanics to describe deformed bodies. So a continuum mechanics framework I'm using the word continuum mechanics, but we're going to be using it down at the micro scale. So I want to draw a little chart here as we talk about scales and how we model things before we start off. So for down, we've got nanometers, micrometers, millimeters. So for down at nanometers, we want to model deformation. we're probably going to be using density functional theory. We've got individual atoms. Then the next kind of size scale up, we're going to be using molecular dynamics. And then the next size scale up to about microns, we're going to be using dislocation dynamics. And then this range from about micron up, that's where we're going to be using continuum mechanics. So this is going to work for a lot of the deformations that we're talking about in the class. But when we're down in this range, we're going to be talking about explicitly modeled microstructures. And when we're a millimeter and above, we're going to be talking about averaged microstructures. So that brings me to my next point, talking about material points. So that's where we're going to start off with our continuum mechanics review. Material points and mappings. So we have our body, and it has forces applied to it along with boundary conditions. And if we look inside, if we're working in a continuum mechanics framework, this body is made up of a material point. That exists in a position of space. And I'm going to use a big X to describe the position of this material point. And so this X is a vector that describes the position of material point here. And let's be careful. This is a vector describing the reference or initial position of the material point. And so if we're working down at the micro scale with an explicitly modeled microstructure, this material point might have a crystallographic orientation. It might have different slip systems in it that are related to its crystallographic orientation. Whereas if we're at the continuum scale, the response of this material point might be the average of several different crystal orientations. And this material point, as the body deforms, is mapped. So I'm going to use chi to a new position that I'm going to have a small x. And that's a vector describing the current position. So every single material point in the body has an initial position and a current position. And the mapping chi describes this transformation of all the points. So kind of a simple example. So an example mapping. So we're going to stretch a cube in one direction. It's going to get taller. After our mapping. To describe that, we're going to take each coordinate point, so x1, x2, and x3, and we're going to relate those to their initial configurations. So since we're not stretching along the one coordinate direction, the current and the reference positions are the same. Since we're stretching along the two direction, we're going to keep it simple. We have a simple linear relationship that stretches the reference coordinate into the current coordinate, and then the third coordinate doesn't change. So this is just a simple example of a mapping for all the material points in this body. And sometimes I think it's just easier to actually see an example rather than something abstract like this mapping, written the same way. This is a concrete example. This is just a description of chi mapping the reference coordinates into the current coordinates. So I'm going to take a quick detour and talk about tensors. So in this class, we're going to be dealing with tensors quite a bit when we're just talking about deformation. Not so much on the X-ray side, but on the solid mechanics side. What's important to remember, explaining my notation a little bit, is that so a tensor is a quantity that does not change with a change of basis or a coordinate transformation. And so this is my definition, but there's lots of them out there, and sometimes they get pretty murky. You'll hear definitions like if it rotates or transforms like a tensor, it is a tensor. This is my best way of paraphrasing that. And what that means, and what will be shown in what I'm going to try to keep straight in my notation here, is that if I do something, I have, say, a vector x, so this is a rank 1 tensor. I'm going to put an underline under it. And what that means is that this tensor quantity has a series of components attached to a basis. This choice as a basis is arbitrary, but this whole single unit here, this is a tensor. And so I'm going to try to be careful, and I might be talking about one side being the components of a tensor, and the basis in which those components are expressed. And like I said, it doesn't matter which basis it's expressed in. We can express the components in a different basis marked by this apostrophe here. But these are all the same thing. But if we look at these three numbers and these components, they're going to be different. We need to know the basis too to be able to express the full tensor. And I'm going to try to be very careful here, because in this class we're going to be moving back and forth between lots of different bases, whether it be the lab, or whether we have a basis attached to a moving sample, or we have a basis attached to a crystal that's rotating inside the sample, which is now the samples, and then the sample's moving too. So we're going to have to be very careful between and keep these all straight. So back to continuum mechanics. So I'm going to talk a little bit about deformation gradient. before I get there, I think it's important to talk about, so I talked a little bit about mapping, but there's a few rules about these mappings. And I'm going to paraphrase a little bit, but I think some of the most important ones is that the mapping has to be halving, which has a very formal definition about lines, parallel lines staying parallel. But what's important to remember for an halving mapping is that material points, or at least how I think about it, is material points don't cross each other. Now you can imagine that you have a problem in fluid dynamics when you're looking at fluids because those material points cross all the time. So you can't come up with a nice mapping from the reference to the current position, material point positions. The other important rule is it has to maintain compatibility. Which I kind of think of, there are no holes. And so, some of these rules are a little bit why, when I drew that chart earlier, why continuum mechanics kind of break down, why we don't use continuum mechanics down at the atomic scale. If you're a material scientist, and you think about dislocations a lot, something like compatibility should make you kind of uncomfortable. Because a dislocation, by definition, is an incompatibility in the crystal. So somehow we're doing something where we're taking a whole bunch of incompatibilities and making it compatible in deformation. So at some point that averaging breaks down. But since we follow these rules, we can define something called the deformation gradient. And what that is, it's the gradient of the reference position taken by the current position, or of the current by the reference. And so, what does this really mean? This means that if we go down to a small enough size scale, there's a point where we can treat our mapping like a linear transformation. This F is a linear transformation. And so when I think of a linear transformation, at least in this context, I think of something that stretches and rotates line segments. So we can have small line segment, dx. And if we apply the deformation gradient, we get its new stretched line segment, or we can have the line segment simply rotate, or a combination of the two. And why I bring this up, this idea of stretching a line segment is something that we're going to do later on in the class, is we're going to stretch the crystal lattice. So we're going to take a volume of crystal and we're going to stretch the directions between atoms. So that's how we're going to describe our deformed lattice. So we're going to have a, and talking about this stretching and rotating, our deformation gradient can be decomposed directly into its stretch and rotation components. And this value V is known as the left stretch tensor. R is a rotation. And U is the right stretch tensor. So these operations consist of, first, this one on the left, first rotating the line segment and then stretching it, while as on this side, we stretch the line segments and then rotate them. What's important to remember is that splitting up the deformation this way is something that we've done mathematically, but when a body's actually deforming, they're stretching and rotating at the same time. These aren't sequential operations during deformations. The last thing I want to bring up is that if the deformation is small, we can make a few approximations about those stretches and rotations. So if the deformation is small, the left stretch tensor is about equal to the right stretch tensor, which is about equal to identity plus the infinitesimal string tensor. So I think this is the strain tensor that I think most of you are familiar with. But what we're going to be doing a lot in the class is we're going to be taking the strain and adding it to identity and using that to deform the crystal lattice. The rotation tensor during a small deformation can also be approximated by the identity tensor plus an infinitesimal rotation. So this is this is symmetric.
Is that an omega or a W?
That's a W. and that's antisymmetric. So that's it for our quick little continuum mechanics review. And so we're going to come back to this in a couple weeks. But what's important to remember is that we're going to be using tools like linear transformations to deform the crystal lattice. So the last thing that we're going to talk about today is coordinate transformations. And why we're talking about this, I mentioned it briefly, is that we're going to be moving between different coordinate systems. And I also want to review this because we have lots of users here who get confused about the difference between rotations and coordinate transformations all the time. And so if you're programming these things up and coding these things, getting those confused can really, really cause you a problem. And I think sometimes these are moved through pretty quickly, but I still spend a good deal of my time hunting down problems with coordinate transformations. So all a coordinate transformation is, and let's be careful. So a coordinate transformation, and I'm going to have to switch to indicial notation here, is a set of numbers which can help us move from one basis to the other. A coordinate transformation is not a tensor. Those rotations that I was showing before, that was part of the deformation gradient that changed line segments around, that was a tensor. And all a coordinate transformation is a set of cosines, or some dot products, between the two different bases. So I'll have this apostrophe here that's going to mark the new basis and we're going to take a dot product with the old basis. And so this coordinate transformation, as is written here, is 9 numbers. So the first component of this coordinate transformation, so 1, 1, is the first basis vector dotted with, in the new coordinate system, dotted with the first basis vector in the old coordinate system. And I also want to point out here that this convention that we have here, where we have the new basis first and the old basis second, is an arbitrary choice. So when someone gives you a data set that has a whole bunch of coordinate transformations in it that says maybe what the collection of crystal orientations are, you have to make sure to ask the person giving it to you whether or not they're working, the convention they're using is new basis times old basis or old basis times new basis. In this class, we're going to use new basis times old basis. And this is going to be one of a couple of times in the class where I am going to maybe point out something that can cause a big problem as you're processing data. So this is one right here. And so what do these coordinate transformations do? These coordinate transformations can help us change the components of our tensor from one basis to another. Like I said earlier, we may have a vector A, which is comprised of its components in one basis, attached to its basis vectors, which is also equal to its components expressed in another coordinate system over here. But remember, these two things, these are the same object. What we can see is if we take a dot product, I'm going to put the new basis on this side. We take a dot product of the bases on both sides of the equation here. Be careful. We take the dot product on each side, and what we find is if we take the dot product of one basis with itself, we get the Kronecker delta. And if we do the dot product of the new basis times the old basis, we get our coordinate transformation. Careful. And the Kronecker delta just switches around the indices here. And we find this equation, which relates the components in the new coordinate system, the components in the old coordinate system. So now, if you're coding this thing up, if you're cycling over indices, you can do a for loop, but we can also write this out in matrix form. We can take the components. This is a 3x1 vector. We've got our transformation. We multiply it by the components in the old basis. Similarly, for a second order tensor, something like stress, strain, or deformation gradient, the transformation looks something like, I'll use stress here. So in our new coordinate system, how I always remember is that the components in the new coordinate system end up being the first indices of our transformation matrices. So we have 2 for a second order tensor. And if we have a fourth order tensor up here, and also our matrix forms. Transforming vectors. So we've got our components of our stress tensor in the new frame, 3 by 3. We've got our coordinate transformation. We have our components in the old frame. And on the other side here, we have the transpose of our coordinate transformation. In fourth order, which we'll be dealing with because the stiffness of a crystal is a fourth order tensor. L. So this coordinate transformation is tricky. This one does not have a matrix form equivalent if you're directly transforming it as a fourth order tensor. So to code up and actually calculate this kind of thing, it's going to take you about 5 sheets of paper, or you have to type, or you have to code up a for loop. There is no matrix equivalent. So the last thing I want to do today is a short example that I think highlights the differences between a rotation matrix and a coordinate transformation, and how you can get in trouble if you're not being careful. And I can't emphasize enough how tricky this can be, how much trouble you can get into. So when I like working with coordinate transformations, I like working slow and steady. So what I'm first going to do in my problem, laying things out, is I'm going to establish a basis. And this problem is we're going to be rotating an object. And then transforming to a coordinate system attached to it. So my steps are going to be, I'm going to establish a basis. I'm going to rotate the object. Then I'm going to establish a new basis. And then I'm going to determine the coordinate transformation. So I have a cube sides are of unit length. And I'm going to mark 3 vectors along the sides of the cube. So I'm going to have A01, A02, and A03. And I'm going to rotate this cube about the vertical axis, which is parallel to A02. So the first thing I'm going to do is I'm going to establish a basis. So I'm going to pick a convenient set of basis vectors that are parallel to A01, A02, and A03. I'm going to label them at 1, and I'm going to put an L here, because I'm going to call this the lab coordinate system. And in this convenient coordinate system I've picked, the components of A0L, 1 or 1, 0, 0, at L2, 0, 1, 0, A0L, 0, 0, 1. So this seems trivial, but I'm being careful here. So now, step 2 is I'm going to rotate the object by this angle omega. So the rotation tensor, which is going to rotate this cube, is going to be expressed in the lab basis. So this is tensor R, second order tensor. And the components in the lab frame is we're going to have counterclockwise being positive. It's going to be cos omega, sine omega 0, minus sine omega squared. Okay. And so now I'm going to rotate. As the cube rotates, these 3 vectors are going to rotate, and I'm going to define new vectors A1, A2, A3. A1, and we got to be careful here. We're still in the lab frame. So we're going to have cos omega 0 minus sine omega. A2 0, 1, 0. And A3 in the lab frame equal to sine omega 0 cos omega. So I've now rotated the object. And now, step 3, I'm going to establish a new basis. This is trivial, but I'm going to be careful. So I'm going to establish a new coordinate system, which is the sample frame. And E hat S1 is going to be parallel to the new A1. E hat S2 is parallel to the new A2. E hat S3 is going to be parallel to the new A3. It's a trivial step, but I've talked through it. And now the last step is we're going to calculate the coordinate transformation from the sample frame to the lab frame. So our transformation A from sample to lab is equal to the dot product of the new dotted with the old basis. And what's nice is that's equivalent to dotting the rotated vectors with the unrotated set. And so I worked through actually evaluating these dot products, and when I was done, remember this, again, this is not a tensor, but the 9 components I got of this transformation matrix were cos omega 0 minus sine omega 0, 1, 0, sine omega 0, 1, cos omega. And what's interesting about this, if you look at what the components were of our rotation components in the lab frame, this did not equal our transformation from sample to lab. They're close, but they actually end up being a transpose of each other. So this seems trivial here, but if you actually did this incorrectly and you coded this up, you'd have, yes?
Because an L in the first EI.
Oh, thanks.
No.
Yes.
But is it from the sample to the lab?
Sample to, oh.
You said from the sample to the lab, S comma L.
Sorry, lab to, sorry,
Good.
lab to sample. I apologize for that. I've been off.
Then this makes sense.
Yes, I apologize. Let's keep taking notes. I apologize. This is lab to sample.
Great.
Sorry about that.
No, but your point's good. Really
Right,
good.
but
Really important.
Yeah, we just have to be really, really careful here. So that's why I stopped and slowed this down. And so just sneaking under the time limit for today, which is good. Next week, we're going to be talking about parameterizations of rotations and coordinate transformations. And then I swear we're done with that for a while. We're going to do some basic crystallography. And we're also going to talk about the reciprocal lattice with that. That's going to be the last part of our tool kit. Before we get going. And then we're going to get there. Then we're going to talk about Bragg's law. And diffraction. So we're going to get down to business by the end of lecture next week. So if you have any questions or comments for me, please, you can send me an email and make suggestions. I'm happy to hear it. This is an experiment. So thank you all for tuning in, and have a nice evening.